Hello, AP Calc students. I hope that you can hear me okay. My name is Mr. Rich. I am going to be doing another version tonight of This Week in AP Calculus. And this week what we're going to be doing is taking a look at Unit 2. I'm going to be doing a test review that's going to cover the first half of Unit 2, which really is derivatives all the way up to but not including the product and quotient rule. So we'll be covering how to find a derivative using the limit definition of derivatives. We'll be talking about the relationship between continuity of a function and the differentiability of a function. And also, I'll be doing some derivatives of functions using some basic rules such as the power rule and some of the other rules that we use for trig functions, for natural exponentials, natural logs. So if you are watching live, be sure to check in the chat. Let me know that you're here. And if you're watching on a replay, do the same. And we're going to jump right into it. So I'm going to share my screen, and I'm going to work through some problems, basically, and do some teaching as we go through these problems. And if you have any questions, if you happen to be watching live, feel free to drop me a comment down below, and I'll try to catch those. All right, so let's get started. I'm going to add my screen here, and we shall get started. Let's see if we can make this work. I think that's it. So this is what I am calling Unit 2, Part 1. That's basically what we're covering tonight. So let's hop right to it. Okay, so here is our first question. What we want to start off with is how to calculate the average rate of change of a function over an interval. So I've chosen a problem here that is a trig function, 2 cosine of x over 2, and we want to find the average rate of change between the x values of 0 and pi over 3. So that's what we're going to do. Now, what is average rate of change? So average rate of change, as you have hopefully learned up to this point, is when we have some function f of x, and we decide over some given interval, which I'm going to call from a to b, we want to know the average rate of change of that function. And the average rate of change is really the slope of the secant line that would pass between those 2 points on the curve, right? And this was really where we started that's a really bad secant line, but you get the idea. But this is where we really started our discussion of a derivative, because a derivative is the slope of a tangent line. So we started off with the slope of the secant line, and then we let that distance, if you remember, that we called h between those 2 points, we let that go to 0. So we used a limit to actually define the derivative, which is the slope of a tangent line. And but nonetheless, we can still, without calculus, calculate the slope of a secant line by simply using a slope calculation, right, between those 2 points. And that would be f of b minus f of a. And then we would divide that by b minus a, because if we look at our 2 points right here, right, this distance, the rise, is the f of b minus f of a, and then the run would be the b minus a. So in this case, our average rate of change between 0 and pi over 3 would be 2 times cosine of pi over 3 divided by 2, which would give us pi over 6, and then minus 2 times cosine of 0 over 2. And then we would be dividing that by the difference in our x values. So that would be pi over 3 minus 0. So that expression there is the average rate of change. It would be the slope of the secant line that goes between x equals 0 and x equals pi over 3. Well, we can go ahead and simplify this, because on our unit circle, we know that that's going to be root 3 over 2, right? So this is 2 times root 3 over 2. And then cosine of 0 is 1, right? So this would be a minus 2 times 1. And then this down here is obviously a pi over 3. All right, well, we can simplify this further. This would be root 3 minus 2 all over pi over 3. And we could write that in its simplest form, maybe as saying 3 over pi times root 3 minus 2. And so that would be our average rate of change of this function 2 cosine x over 2 between 0 and pi over 3. All right, so let's carry on. Let's go and see, make sure that we get that right. So these 2's cancel, root 3 minus 2. I think we got it. So let's move on. Now, the next question is to evaluate a limit. And this right here, you could recognize this as the limit definition of a derivative that is actually being used to evaluate a function for its derivative at a certain x value. So I'm going to write down the limit definition of a derivative right underneath this so that we can maybe draw some conclusions about what we're looking at. So this is the definition of a derivative of f of x. So what it is the limit as h goes to 0 of f of x plus h minus f of x. So what we can see here is that we do have an f of x that's equal to 2. Okay, so we can see that there's a 2 in place of the f of x. Now, what we also see here is that it looks like there is an h, a value right here of 8. And actually, you know, this, let's see, we want this to be x plus h. And I believe this is incorrect, that this should be 8 plus h is how that is supposed to be. I think that is a mistake there in the problem. So what we're looking at here is that there is an x value of 8. So this really is a derivative of some function evaluated at x equals 8. Okay, now what could that be? Well, we're looking at the function here, right? And so that would be the cube root function. So what we could really say is that what we're looking at here, this cube root of 8 plus h minus 2, looks to be the f of x was the cube root of x, and then we wanted to evaluate that at an x value of 8. So really what this whole limit is f prime of 8, where f of x is the cube root of x. So what I'm going to do, instead of evaluating the limit, I'm instead recognizing what the limit is representing. It is representing the derivative of x to the 1/3 power. So I'll use my rules of derivatives to take that derivative, and that would be 1/3 times x to the negative 2/3 using my power rule. And so that then would be my derivative. But the limit that I'm trying to evaluate, as we said, was evaluating it at 8. So f prime of 8 would be 1/3. Now I'm moving this down into the denominator and then replacing the x with an 8, and that would be to the 2/3 power. So the question then becomes, well, what is 8 to the 2/3 power? Well, the cube root of 8 is 2, and 2 squared is 4. So this would be 1/3 times 4, or 1/12. All right, so typically on any AP exam, you're going to be asked to evaluate a limit that is written to represent the derivative of a function. And so based on the symbology and the notation that they're using in the limit, you want to then try to determine what function it is taking the derivative of and at what value. And then you can use your rules of derivatives to evaluate the limit rather than actually evaluating the limit with the methods that we learned from Unit 1. Okay, so that is an example there. I think I have one more example later on. The next problem here says find the equation of the tangent line to the following function at x equals 4. So we have to find the equation of a tangent line. So when we're finding equations of tangent lines, we are always going to use the point slope form for a linear equation. And what we need is we need to find the slope of the tangent line. Well, that's going to be the derivative of the function. In this case, it's g of x. That's going to be the derivative evaluated at the x value of interest. So that's going to be g prime of 4. Then what I need to do to complete my tangent line equation is I need to find the point of tangency, x1, y1. So x1 comma y1, that's going to be the point of tangency. And I'm going to get that simply by saying that, well, I'm going to evaluate my function when x is 4. So that would be 4 comma g of 4. So the two things I need are g prime of 4 and g of 4. So let's take the derivative first, g prime of x. And the derivative of the natural log of x is 1 over x. So this derivative is going to be 2 times 1 over x, or 2 over x. I'm going to evaluate that now at the requested x value here, x equals 4. So that's going to be 2 over 4, or 1/2. So that's going to be the slope that I'm going to put into my point slope form to come up with my tangent line equation. The other thing that I need is g of 4. So that's going to be 2 times the natural log of 4. I think I'll move this 2 up into the exponent. I'll call this the natural log of 16 using the power rule of logarithms. And so now I know that my point of tangency is 4 comma natural log of 16. And therefore, here's what my tangent line equation is going to look like. It's going to be y minus the natural log of 16 is equal to 1/2 times x minus 4. And I can leave it like that. I typically tell my students to go ahead and move this negative natural log of 16 to the other side. Do not distribute the 1/2. Leave it just as it is, plus the natural log of 16. And that becomes the equation of the tangent line at x equals 4. Next, if f of -3 is 4 and f prime of -3 is -2, find the equation of the tangent line to f of x at x equals -3 and use the tangent line to approximate f of -3.1. So I'm going to use this as my point of tangency. I'll abbreviate that POT. And this over here, this -2, is the slope of the tangent line. And so I'm going to come up with a tangent line, again, using point slope. That's my template that I use for building any tangent line or normal line equation. And what do I put in? Well, the slope of the tangent line is a -2, and the point of tangency is -3, 4. So this is going to be y minus 4 is equal to -2, and then x plus 3. I will move the -4 over, and there we go. So that's my tangent line equation. So let's just take a look at what we're talking about. So suppose there's some unknown f of x. Okay, I have no idea what the function is because they didn't give us any information about that. However, if I do come out to, let's call that x equals -3 right here. And what we just determined, when x is -3, there would be a tangent line, right? That's going to come down, and it's going to have this equation. So what I can do now, if I'm trying to estimate what the function value is at a negative 3.1, which would put me over here, I'm just going to find out what's the y value on the tangent line itself as my estimate for what it would be on the actual function itself. And of course, in this case, that's the only option I have to come up with f of negative 3.1, because we don't have any idea what the function f of x is. Right? All we were given were these two pieces of information. But I'm going to use this equation right here. So I'm going to say that f of negative 3.1 is approximately equal to negative 2 times negative 3.1 plus 3 and then plus 4. Well, this is a negative 0.1 here in these parentheses, and negative 0.1 times negative 2 is a positive 0.2. So this would be 0.2 plus 4, or we would say it's f of negative 3.1 is approximately equal to 4.2. And that's what we call a linear approximation. Let's move on to the next one. Here I've got some functions that I'm going to just use some rules of derivatives to take the derivatives. First one, I'm just using power rule and also the sum and difference rules, which says that if I'm taking the derivative of a function, I can really just take the derivative term by term. Separate and distinct from one another, I can take these derivatives. So the derivative here is f prime of x is 3 times 2, which is 6, times x to the 3 minus 1, or x squared. This next term would be 2 times 3 is 6, and that would be x to the first power, and the derivative of a constant is 0. All right, next, g prime of x. This just requires me to know the derivative of the sine function, which is cosine. So this is 3 cosine x minus 6x squared. Easy enough. Next one, need to do a little bit of work on this one so that I can use the power rule. Now, we could use the quotient rule. Of course, in this, I'm not covering the quotient rule. That's going to be next week. But what I can do in order to use the power rule is I can break this function up into two separate fractions. I'm also at the same time going to convert that radical into a rational exponent. So it looks like this. I will go a little bit further here, and now using my rules of exponents, this is really 5x to the minus 1/2 power, because this is, and that'd be a positive 1/2. This is 1 minus 1/2 by the quotient rule of exponents. And then here I'm going to use my negative rule of exponents, which says that I can take that x to the 1/2 from the bottom and move it up into the top. And ordinarily, we don't like to make positive exponents negative. We're trying to usually go in the other direction. But in this case, we want to move that up into the numerator so that I can use the power rule when I take the derivative. So now I am ready to take the derivative using the power rule. So this would become 5/2 x to the negative 1/2. This would become positive 3/2 x to the negative 3/2. As I reduce that exponent by 1, it makes it negative 3/2. Finally, what I will do is move these negative exponents down into the denominator to make them positive. So this would be 5 over 2 times x to the positive 1/2 plus 3 over 2 x to the positive 3/2. And that is my derivative. The next one, I am going to do a little bit with this, right? Because the only thing that we've learned so far is really what is the derivative of the natural log of x, not natural log of x to a power. So I'm going to move that 3 out to the front using the power rule of logarithms. So I'm going to rewrite my f of x as 5 times tangent of x minus 3 times the natural log of x. Now I'm ready to take the derivative. So f prime of x is going to be 5 secant squared x, because the derivative of tangent is secant squared. And the derivative of natural log of x is 1 over x. So this would be 3 minus 3 over x. 3 times 1 over x, or 3 over x. That is the derivative. Let's go to the next one. So what I'm going to do here is I'm going to use my product rule of logarithms, right? So I can separate logs of products by addition. So I am going to rewrite this as the natural log of x squared plus the natural log of e to the x. I can work a little bit more with this and call this 2 times the natural log of x by the power rule of logarithms. And this one simplifies to just x, right? Because this is log base e. So to simplify this, I'm recognizing that the natural log is log base e of e to the x, that is just x. These two will cancel each other out, leaving me x. Now, that is my y. That is my function. I'm ready to now take the derivative of this, and this is going to be 2 over x, because the derivative of natural log of x is 1 over x, and the derivative of x is just 1. All right, let's carry on. We are next going to look at another problem similar to the one that we did above, but this is using a different definition of a derivative. So what I am going to do here is I'm going to write below here one of the definitions of a derivative. We called it f prime of a. So it's the derivative of x evaluated at a. So f prime of a would be the limit as x approaches a of f of x minus f of a all over x minus a. Now, what do we have here? So we kind of want to match this up. Now, I'm going to rewrite this, and I'm going to swap the order right here. I'm going to call this the limit as x approaches 9 of a negative x squared plus 9, or 81, I should say. That's going to be plus 81. And then this is x minus 9 right here. Now, this I could solve this pretty easily, I think, by just doing difference of squares on the top. But what I want to show you here is that this right here, this 81, that is the f of a. Okay, so that's f of a 81 is a positive 81, and this is the f of x. Okay, so this really is, this is the derivative of f of x evaluated at 9, where f of x would be the function negative x squared. So what am I going to do? I am going to find the answer to this, I am going to take f prime of x. All right, so again, I want you to notice what I did was using my knowledge of this particular definition of a derivative. I'm recognizing that this is the derivative, this limit is the derivative of f of x equals negative x squared evaluated at x equals 9. So what I can do is take the derivative of f of x using the power rule and then evaluate it at 9. So that's negative 2 times 9, or negative 18, like that. Now, could I have just straight up evaluated that limit? Yeah, I definitely could have, because I could have separated this out by negative x. Let's see, we could have done this as 9 minus x, 9 plus x, factored out a negative 1, and we would have got to the same answer, negative 18. Okay, but for this test, what you have to be able to recognize is limits that are from the definition of a derivative that are applied to specific functions, and then use your rules of derivatives to find the limit. Okay, I think I got another one here. Yeah, let's take a look at this one. So again, this looks like the limit definition of a derivative. And so here is the x value, right? So this definitely is the derivative of some function f of x that's being evaluated at -1. Now this whole entire thing right here is f of x plus h. So it looks to me as though the f of x function that would have created this limit definition of a derivative would have been x cubed. Okay, and that kind of makes sense here because this plus 1 would have to be f of -1. Okay, and since this has to be f of x plus h minus f of x, that would be minus that -1 that would have created, because f of -1 is a -1. So if we applied the limit definition of a derivative, we would have f of x plus h minus a -1 or plus 1. So the easiest way to evaluate this is really just to take the derivative. F prime of x is 3x squared, and then let's evaluate that at -1, which would be 3 times -1 squared, or an answer of 3, like that. Okay, now before we leave this, I want to put this back up, right? That f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. You will more than likely not be given this on a test. It's something that you need to know. So let's just test this and make sure this works. If this was my f of x, and I wanted to find its derivative at -1, I would have said this. I would have said, okay, f prime of -1 is equal to f of -1 plus h. So I would have said, well, that would be -1 plus h cubed minus f of x. Well, that would be f of -1. So that would give me, we already determined up here, right? F of -1 right here is a -1. And then that would all be over h, with, of course, not leaving out my limit. So this would be the limit as h goes to 0. And indeed, that minus a negative makes that a plus. And so you can see that that is indeed where I started. Okay, so it's kind of working the limit backwards, determining what the function was and what x value it was, and then using your rules of derivatives to more easily calculate the answer. All right, next question. Use the limit definition of a derivative to find the derivative of the following function. So the limit definition that I'm going to use here is this. F prime of x is equal to, I'm writing this down probably the 4th time now, as h goes to 0 of f of x plus h minus f of x all over h. Now, it kind of goes without saying that if I tried solving this with direct substitution at this point, I do get 0 over 0, so I have quite a bit of work to do. So what I have to do is I have to first find f of x plus h, and that's going to be a negative x plus h squared plus 5 times x plus h minus the entire f of x, which would be negative x squared plus 5x, and that's all over h. So my task at this point is to expand that numerator and then combine the like terms with the hopes of canceling that h down on the bottom, so I could then finally plug 0 in for h. Can't plug 0 in for h right now because I'm still going to get 0 over 0. So let's go through the algebra process here. So I've got the limit as h goes to 0. I am going to combine a few steps here at once. I'm going to go ahead and expand this x plus h squared and distribute that negative. So that's going to be a negative x squared negative 2xh minus h squared. Distribute that 5. I get plus 5x plus 5h. Distribute that minus, that's going to give me plus x squared minus 5x. And that's, again, all over h. So things simplify quite a bit. As you see, I've got two pairs of terms that are going to cancel. The x squared, negative 5x, 5x. This leaves me 3 terms. They all have a common h. I'm going to pull that h out, leaving me negative 2x minus h plus 5 all over h. H's cancel. I can now substitute 0 in for h, and I get my answer of negative 2x plus 5. That is my derivative that I found using the limit definition of a derivative. Now, if you know the rules of derivatives, you realize what the derivative is in about 2.5 seconds rather than going through this whole process. That this derivative, using the power rule, is a negative 2x plus 5, which is what we ended up with. All right, but oftentimes your teacher is going to have you on your first unit test on derivatives show that you can use this limit definition of a derivative to find a derivative. All right, next question. Find all points on f of x that have a horizontal tangent line. Well, horizontal tangent lines would be tangent lines that have a slope of 0. That's horizontal lines have slopes of 0. So the exercise here is really finding the derivative and setting your derivative equal to 0. The derivative of 2 is 0. That's why that drops off here. And now I'm solving this for x. Now, don't forget, if you're solving a linear equation, or I should say a nonlinear equation, you want to solve for x by factoring. You don't want to lose any of the solutions by dividing both sides by x. You would not do that. What I am going to do here is factor out a negative 3x. So when I do that, that's going to give me an x minus 2, x minus 2 equals 0. And then what I'm going to do is set each of those equal to 0. Right? And I get my two solutions here. At x equals 0, x equals 2. So those are the x locations on the function where I should have horizontal tangent lines. Now this says find the points, right? So what I want to do is I do need to find f of 0, which is 2. And I do need to find f of 2, right? I'm using my original function up here. So that's going to be minus 2 to the third plus 3 times 2 squared plus 2. That's going to be negative 8 plus 12. That 2 squared is 4. 4 times 3 is 12 plus 2. That looks to me to be 6. So it looks like my answer is 0, 2 would be one location of a horizontal tangent line, and the other one would be 2, 6. Like that. All right, moving on. Determine, and this really is my last problem here that I'm going to work tonight. And it has to do with continuity and differentiability of a piecewise function. So I want to just review real quick what it is when we say a function is continuous. This really comes from the previous unit. So for a function to be continuous, right, f of x is continuous at x equals c if the following three things are true. f of c must exist. Number 2, the limit must exist of f of x as you approach c, which really also means another statement that we can say, right? The limit's only, let me say it exists. That limit must exist. Now, for the limit to exist, what has to be true is the limit as you approach c from the right must be the same as the limit as you approach c from the left. So that is another way of stating number 2. And then the third thing that has to be true is these two things from numbers 1 and 2, they have to be the same thing. So it has to be that f of c is equal to the limit of f of x as x approaches c, and that has to be a real number. Right? That's kind of implied, but I'm going to state that, right? It has to be a real number. So when I look at this function, and they did ask me about continuity and differentiability at a specific value at x equals 3. But one thing that I do know about this piecewise is that both pieces of it, from the left of 3, which is x squared, and from the right of 3, 6x minus 9, those are continuous functions over their entire domain, which is all real numbers. So the only place f of x could be discontinuous would be where the two functions are meeting at x equals 3. So if you look at these three requirements, the function certainly does exist at 3, because this says that when x is equal to 3, I would be evaluating that to be 9. So the function does exist. Now, the question though becomes, does the limit exist at 3? So that's really where we're starting our analysis on this for continuity. So what I would be doing is I would be taking my left-hand limit. So I'm going to, here's my solution. This is the start of my solution here on continuity. So I would wonder if the limit as I approach 3 from the right, I want to know what that number is. So from the right, I would be using this function here, and through direct substitution, that would be 6 times 3 minus 9, which is 9. Then I'm going to evaluate the limit coming in from the left-hand side as I approach 3 from the left. And coming in from the left, I would be using this first function, and through direct substitution, I get 3 squared, and that's 9. So I can say that this function is continuous. Okay, so f of x is continuous at x equals 3. And then I give a because statement. Because, and my because statement is going to be this statement right here. Because f of 3 is equal to the limit as x approaches 3, and that value is 9. So it is continuous. Now, let's talk about differentiability. How do we determine whether a function is differentiable? So I'm going to give you two statements here. So, f of x is differentiable at a particular value of x. Is differentiable at x equals c if, number 1, the function f of x must be continuous. So if I've already determined must be continuous at x equals c, so at my point of interest, at my x value of interest, if the function, hey Neek, good to see you here, buddy, f of x must be continuous at x equals c. If I already determined that the function's not continuous at x equals 3, then I can say that it's not differentiable either, because that's the requirement, right? If a function is not continuous at a certain x value, then for certain the derivative does not exist there. Now, where could a function not be differentiable? The four things that we really looked at are, number one, at a corner. Even though the function might be continuous, it might not be differentiable. It would not be differentiable if there is a corner at that x value. Secondly, if there's a cusp there, even though the function would be continuous at that cusp, the derivative would not exist at the cusp. Or number three, if there is a vertical tangent line. And number four, if there's any discontinuity. If the function is discontinuous, either a removable, a non-removable, or an infinite discontinuity, then the function just does not have a derivative at that x value. Now, in this particular case, the function is continuous. We already determined that, but that doesn't by itself show that the function is differentiable. So what I have to do now is I have to show, so number two, that's my first check, must be continuous at x equals c. The second thing that we have to do is check to make sure that the limit as I approach c from the right, the limit of the derivative must be equal to the limit of the derivative from the left as x approaches c from the left. So what I'm going to do here is that's what I'm going to check next. So my solution on differentiability for this particular function is to evaluate the limit as x approaches 3 from the right of the derivative. Now, what is the function's derivative to the right of 3? Well, to the right of 3 right here is this function, and that derivative is 6. Okay, so that is equal to simply 6. It's a linear function with a slope of 6, so the derivative is obviously 6. But then I want to calculate the limit of the derivative as I approach 3 from the left. The derivative of 3 from the left is 2x. Well, let's write it this way. I'm going to write it. I could go and skip this step, but I want to write it for clarity. So basically what I'm doing is I'm taking the limit as x approaches 3 from the left of the derivative, which would be 2x. And by direct substitution, that is 6. And so I can say that f of x is differentiable at x equals 3 because, and that is because the limit as x approaches 3 of the derivative is equal to 6. So that limit does exist, and that limit is 6. Again, that's the limit of the derivative. Okay, that about covers it. That is all the problems that I was going to cover for today. So I really hope it was helpful. If you did, hit the like button and leave a comment to let me know you were here. And I will see you next week. Now, next week, what I'm going to cover in next week, what I'm going to cover on the live stream is going to be the complete Unit 2 review. So that's going to include product rule, quotient rule, and probably concentrating more on that part of Unit 2, but also touching on the other parts, some of them that we covered here tonight. So be sure to tune in next week, and that's probably going to be at 9:30 next week as well. All right, so thanks for tuning in, and I'll see you next week. Take care.